my learnings over the past couple of years on deploying ML systems 0 to 1, specifically in the case of early stage startups. And I think one thing to note here is that I'm specifically focusing on data plus ML systems because I believe data alone can add value to a business, but without that setup, ML itself will be powerless and will not be able to generate much value. So, to begin with, let's discuss a little bit around what are the specific constraints for early stage startups where you would not find in other companies. The business requirements are changing pretty fast. We are building one product now, and then pretty soon we have to switch over to other things. So we cannot focus too much on a specific problem. The traffic, the scale of the data, and the traffic coming in is not that high, so it's hard to run meaningful A/B tests and get results. We have to really push products out in like pretty small time, somewhere in the range of like 3 to 4 weeks or max like 2 months. There is very little infra support, so we have to kind of build infra as we go for deploying ML models. And the data logging is inconsistent, sometimes missing. We might want to solve a problem and realize that, oh, we're not even logging the data needed to solve the problem. So those are some of the challenges. And I think I would kind of share some key takeaways that you would get from this talk. And first one would be the absolute crucial thing that I found is converting a business problem into the right ML problem. And I think this is along the lines of what Aarshay was just talking about, that when you pick the metric that you want to optimize, then you want to also find the right problem that will solve that metric or that will move that metric. You can get a 95-100% accuracy on a problem, but if it's not correlated with your business metric, it's not going to add value. And one of the litmus tests for seeing if you have that is having a strong offline evaluation setup. We can chat more about that separately. But yeah, and another thing is a common theme that you've probably been seeing around in the conference where better data or features trump ML model parameter optimization. And this is specifically true in the case of early stage products where you don't have a lot of base setup. In addition, I feel that when focusing on data and features gives you more longer term reusability benefits too, which we'll see in a little bit. Another aspect that I feel is very important, specifically in case of startups, is that we should think about building a feature first and an ML model next. So when we are trying to solve a problem, we need to think about, okay, maybe we build an MVP first and then we deploy ML. And this gives us more real estate and more wiggle room to play around, because we can deliver value really fast using an MVP, and then we can implement an ML model as a V2. It parallelizes engineering development and it saves us a lot of time. I'll also go over some like tactile or implementation level learnings if time permits. So just to give you a little bit overview of what Jupyter is. So Jupyter is a startup based out of California. We are running a creator-driven ecosystem wherein we allow creators to come on the platform. We create a shop for them on Jupyter. So if you're a food influencer, you can go on Instagram, you can post a recipe. Your user can just come in and buy that recipe straight away from the platform. So just to give you a quick overview of the engineering team, we have a CTO, a couple of backend engineers, a couple of front-end engineers, I'm the data/ML engineer, and we have an analyst. So yeah, the team is pretty much spread out across the globe, and we're a pretty small team trying to build a product and find product market fit. So to give you an overview of the stack that we have. So first of all, we start with some serving infrastructure. We use fast API-based ML endpoints, deployed service in a Kubernetes cluster, obviously containerize our applications in Docker. In order to do that serving, we need to generate some data artifacts which are stored in Bigquery, CockroachDB, Cloud SQL, cloud storage, all for different kinds of I/O requirements. And then for training or learning, we use again Apache Beam, Cloud Dataflow for running distributed jobs, AI platform for model training. So it's an entirely GCP-based setup. And this is just the ML infrastructure that we're talking about. The other backend application is run in like Kotlin-based JVM environments. And of course, we have then Airflow, which kind of binds everything together and makes sure things run and things are available when we want them to. So next, I would talk about a few applications that we have deployed over the past year or so. And the first major one is around next cart prediction. So what we do is user can come and buy on our platform. As soon as they check out a cart, we give them a second prediction of a cart right away. if you heard the talk of like Jubilant Foods yesterday, I think they were talking about something like a magic card feature. I think that is something that we started off with as a key differentiator of our platform. And we have seen that this gives us very high retained users, we have high lifetime values. It even increases the average order value if we get these predictions right. Next, we use ML in not just user facing but internal applications. For example, new catalog onboarding. So we use DoorDash for delivery, and when we so for DoorDash, we need to like onboard a lot of retailers. Like for example, there's Walmart, there's Safeway. We need to onboard all of their catalogs into our system. We scrape DoorDash, we get a list of things like, for example, we might say a 1 liter Mother Dairy full cream milk. We need to take that string and ingest it into a database wherein what is the unit, the quantity, the name, the brand, the canonical group. Like we have some metadata tagging to be done. And that process was really long and tedious. It used to take us a month to like onboard a new catalog, and we built some human in the loop ML kind of inference systems which brought that down to a week. Assisted recipe creation is another very recent application that we have deployed, wherein so when we talk about a creator, for example, if you create a recipe around a pasta, you will also have to come on our platform and say, okay, this pasta contains these 8 to 10 ingredients, and these are, you have to search the products on the platform and say, okay, these are the products that this recipe contains. And this would take somewhere around 30 to 45 minutes for a creator to do, which is too long. So what we have done is we just deployed a product wherein a creator can just copy the list of ingredients from their blog, they paste it on the app and they hit run, and then we parse that string and we go into our database and we get a product match for every single item that they have. And then their job is just to see if it is correct and make some minor modifications. We are mostly 80% correct, so we have really brought the time down to like around like 10 minutes, 10 to 15 minutes range. And we tried a couple other things, like not all models are successful or drive business value. These are a couple of use cases where we haven't really been able to generate a lot of value yet, but we tried these around personalized marketing and meal planning, but we weren't really able to get user traction here, and we couldn't focus on these for much longer. I think with this overview, I want to kind of get into a specific problem and go through the use case around how we went around solving it and hopefully derive those takeaways out of this case study. So I'm going to talk about the next card prediction problem, which is, so this, I'm not sure is it clear? I hope fully. So basically this is a view of our cart on the app. What you see on the top right is this user buys every Saturday, so delivery for Saturday, September 24. We give them a delivery on every Saturday. Right now it's Friday. This is a view on Friday because they have a day left to finalize their cart. Otherwise, whatever is on the cart gets checked out and it'll be sent to them on Saturday. And as soon as it is sent to them, a fresh cart is generated automatically for them. So you can see here on some parts, it says like predicted by autopilot. That is our model. And there will be some entries which user will make on their own. So what is the user impact? We really want users to minimize the time they spent on grocery. Right now, we have our users tell us that, hey, we were spending hours just like adding the same items again and again every week, and this saves them a lot of time. When we started building this problem, the current solution was really our product team literally spending 40 to 50 hours every day and manually generating these predictions for all of the users. I mean, at that time, we were like really small, like 50 to 100 users. So it added a delay and added a lot of time. So literally the first version, the goal is save those 40 hours of effort, build something which is just as good as that process. Okay. I think you guys have an older version of, you might not have refreshed it, but is it possible to quickly refresh it? Anyways, I'll move on. So system design. So this is the business problem. Now, the way at least I like to think about the problem is, okay, first think of the system before we build it. Like, how are we going to solve this problem? How will the user see the predictions? And let's start from the serving. Let's start from the user side of it, and then we'll see what is needed to build that. So we will generate an endpoint for it using Fast API, wherein as soon as user places a purchase order, that information will come in. we will make predictions for, we will just predict the exact SKU means a product, like a specific product, the exact SKU that needs to be sent, and we publish those results back to the user. Simple, right? And for that, we need some certain artifacts. So the latest information is coming in. We need some pre-aggregated data around the user's purchase history. We need a pre-trained model, which we would, and both of those artifacts will be needed to power that endpoint. How do we generate these artifacts? We create a data pipeline where we have some data logs. We run data aggregations, model training, and these artifacts are created. So this is a pretty vanilla system. This was the first version we deployed, and like in order to build that model was again pretty straightforward. We got into the historical data. We created features, like we created much more, but it's like some of them, what was the number of times they purchased within 1 week, 2 weeks, 3 weeks, and whether they purchase this next week was labeled. So we created a simple model. I think the exact data engineering effort which went into creating these aggregates is interesting, but I think for the half an hour talk that we might not be able to get into that. So I'll skip over those. I skipped over those slides here. And we chose a simple supervised learning model. We got a precision and recall of around 0.6. This was roughly what the manual process was also getting, just slightly better than the manual process. So we were good. We got a green signal from business, and we deployed it. We started like building it. So slowly we were building it. We shipped the model. The metrics looked great, at least initially for the couple of weeks. And we just deployed it, let it run, and we moved on to building other stuff. In a few weeks, when we went back to the dashboards, we started getting some user feedback, and we realized that the model wasn't really working as we intended. There was a long way to go. And then we started looking into, okay, what went wrong? The model was really working. And what we really identified is it was really our growth of the company which led to the poor model performance. And what I'm really trying to say is like we outgrew the assumptions that were present at the time we built the model. For instance, like one of them was, now that we were onboarding new retailers, there were a lot of substitutions going on. Our catalog was increasing, so there were too many SKUs. Our aggregates were very, very sparse. For example, like the same tomato or like a banana, we had like 5 different SKUs with different bundles of bananas and other things. And aggregates we were expecting users to purchase the same exact SKU again and again to be able to capture that repurchase, and that was not really happening. Secondly, we were expanding geographically, so a lot of new users were coming in. The new user will also come with new retailers. We had no context on their products, so we were not able to power any of those applications. Thirdly, when in general these days, I think an interesting stat was posted during one of the talks, wherein they said users, I think around 60 or 70%, something like that, users expect communication around why they are being shown a recommendation, or they want more control over what is being sent to them. And specifically in case of grocery, this was a specific demand or feedback coming back from our users. So we went back to the drawing board. We realized that this is not necessarily a model improvement or a model tweaking problem. It was more of a systematic issue, and we needed a bigger resolution here. So what we decided to do is we created clusters of our products as a separate work. What we did is we went that, okay, these are all the tomatoes are clubbed together into a category called tomato. All of the bananas are called banana, and then whole milk, 2% milk. We just created these categories. The idea behind, or the definition of a category, is that if you buy a product in that category, even if we send you some other product from the category, it should be the same exact thing. For example, if you went and bought like mother dairy butter, and we gave you Amul butter, it's probably be expected to be the same thing, and user to be able to do what they wanted to do with that product. So as soon as we defined that grouping, it essentially meant that we could now learn our aggregates at that group level instead of an individual SKU level. And that was really powerful. To give you some more context, like we have 30,000 SKUs right now, but only 3,000 products. So if we learn our aggregates at 3,000 canonical products, that's the name of the group that we defined. So if we learn our aggregates at that level, we reduce the sparsity by 10x, and that is very, very powerful. Another important thing is, like, since we are learning at a product level, even if a new retailer comes in, We just have to map their products into the right categories, and we have baseline aggregates for them to start running from day one. So this kind of solved a lot of our problems. And to give you an example of, we kind of then needed to put that on as a UI element of how the user would consume all of that learning. And we created this UI element wherein we saw, okay, whole milk is one of the categories. We defined that as a canonical product. We told user explicitly that, okay, this milk is gonna come on February 11th, which is like in a week or in 2 weeks, because users were anxious. They see their cart right now. They want to plan ahead. They're thinking, okay, when am I gonna get this next? They explicitly wanted this information. So we wanted to give it back to them. We are predicting their inventory. So earlier what was missing is there was no way for the user to give us feedback into our prediction. So we said, okay, we are gonna show you what we think your current inventory is. Because at the end of the day, that matters. We will send you something if we think you're running out of it, and if we think you use it consistently. So those are the two things. So first of all is inventory, and second is autopilot. So we also gave them a control on, we think you use this product consistently, so we have kept it on autopilot. If you don't, you can remove it. If there's a product which we think you don't use consistently, you can add it back. And you can give us inventory information. This entire view completely changed the definition of what we were communicating or what we were promising to the user. Earlier, we were kind of telling them, okay, we'll send you this particular product. Now we are telling them, hey, we will send you whole milk every week. We will try to send you the exact SKU which you want, but even if we don't have that, we will send you some whole milk every week. And then there is another view where you can select and prioritize SKUs and such, but less relevant from an ML perspective. And then that particular block, they would be like, see everything what they've purchased, some of the things are on autopilot, and they can give us feedback, control whatever they wanted in the system. So now what does this mean from a system design perspective? Like, how do we power this? How do we power these recommendations and that feedback, predicting when we should send something? So we had to redesign our system earlier. Again, thinking from a serving perspective first on how the thing will be used, and then we will figure out how we build it. So we went on the serving side. We were just predicting SKUs directly. Now we changed our model from predicting an SKU to predicting the weekly consumption quantity of every canonical product. So now what we learn is every week, how much milk do you consume? How much of yogurt do you consume? At an absolute level, you consume 5 liters of milk every week, and that's fair. And you consume 5 12 OZ yogurt every week, and that's what we learned. So we would make, whenever an order comes in based on whatever products were purchased, we would make those predictions and update those views of those, have an estimate on what is the new inventory of those products and the future inventory of those products. Once we have updated those values, then we would select the exact canonical products that needs to be sent in the next order. Because everything is now deterministic. Once we have made that prediction, we know what is going to be in next. Then we select the exact SKUs, and we publish the results out. And in terms of artifacts, now we need to store a couple more things. We changed the model. We need to store historical predictions, because now they are an input into selecting what you need. And then we have to store some more exact SKU purchase stats along the side. And then the training pipelines, I think here, less relevant, just similar stuff, just aggregating data in a different way. So we ended up deploying that, and then what did we saw? We saw we didn't have a massive scale, so we mostly rely on user research. So the users were much happy; they were able to control what they are getting. The new communication system was working. We had good improvements on our actual average or precision and recall of the model in production. But what happened suddenly, during the process of this being deployed, the product's requirement changed. So the VC landscape changed drastically. US was in a recession, funding dried up. This was a purely growth-based product where we were burning money to get users in, and we were trying to retain them using this experience. But we had to change our strategy to more revenue-based, because now we wanted to also make money along with growth. So another step was added before this step in the user acquisition funnel, and the traffic we were expecting to hit this feature didn't really, that didn't really happen. So this was really disheartening at the level, and we spent so much time building all the infrastructure, building the model, and then we were like, oh man, this is nuts. I can't do this anymore. But then we started, we took a step back and we realized that what did we really gain with all of this exercise? It is not just the feature. What we gained was we created this concept of canonical products, which was really, really powerful. Now this mapping itself powers almost every, all of the core components on our feature. Even the new feature we built to reduce our CAC was based out of this concept. Yeah, and then we built a lot of infrastructure. So our infrastructure was Fast API, Cockroach DB, Bigquery, GCS. We built a lot of those integrations, Apache Beam, AI platform. We just like had everything set up. So deploying new products was way faster for us. Like for example, once we have this, it took us like around 3 months to deploy this, but the recipe creation was, we were able to deploy that in like 2 weeks and then get very quick business value back. So again, sharing some of the key takeaways here is again along the lines of what Aarshay was saying earlier. When, especially in case of startups, we cannot lose sight of what is the actual business value that we are delivering to the user, to the business, and we have to build accordingly. And ML systems, and when we are like rethinking systems, if something is not working, we should just like think through the entire system and not just think, okay, which other model can I use or how can I change the model. We have to think from a systematic perspective, if the approach itself is working or not, and maybe we need to just change that and get much better gains than tuning the ML model. Underlying matching, or like modifying our data mappings and underlying data has much longer term dividends as compared to pure ML optimizations. And again, like designing, we should always think about designing the feature first, ML model next. And I think this specific thing is relevant for startups because, for example, when I went to Spotify and started working on ML, that is because somebody else spent the time to build all the infrastructure required to even start deploying ML on a problem. So now that we have all of this base setup, now we are in a position after a year that we can go on and build V2s and improve those exact ML models that we have there. Right now, they're all very basic, very simple ML formulations. Haven't really spent time in tuning the models. Just a quick and dirty thing has been deployed. And to be very fair, a lot of this, even when working at Spotify, I had to do a lot of the same stuff around first setting up an infrastructure, running A test before running a B test, and such. Yeah, same thing. Yeah, and then some just sharing some tactile challenges, which means like implementation level details, almost which the things which I struggled and I fixed. For example, historical. So in the autopilot case I was talking about, we need to generate repurchase stats. We cannot generate them every time a request comes in, obviously, but we need to create data pipelines. Now every week you can decide to just store up aggregates and just add new data from that week and create a new aggregate, right? So that is the concept of pre-aggregation, and re-aggregation would mean that you are just re-aggregating everything every week. Although pre-aggregation seems like the right thing to do, it is not always the right thing to do because your data mappings can change. For example, when user purchases a product, any stat at a product level is dead in stone. So we can do all the pre-aggregations we want. But when we join it at a canonical group level, canonical groups are very dynamic. Our ops team is always looking at them and just like changing groups, adding new groups, modifying the group of a product. So we need like very quick feedback. If I pre-aggregate that data, I will just have to go on and rerun my entire historical pipelines every time to capture those updates. So some components we err on the side of doing extra compute, but we aggregate them on every single time we generate the training data. Dynamic production schemas. So, I mean, I think that slide is somewhere in the appendix, but right now, our purchase order information, anything related to what was purchased, how many items were purchased, and all is stored in 13 different tables in the actual production database. And if I build my ML models off of that, those databases are very dynamic. If they need to make a new feature, they just modify something, and it's hard to like block them on ML pipelines because that those changes they need full control over that. So what we do is we kind of create our own mappings of the data set. So any ML pipeline will be based out of a basic ML, a basic data aggregate, and then there's a defined mapping from the prod data to that aggregate. And whenever they change prod data, they can just change one query. As long as the base data, the ML based data works, they can do whatever modifications they want. And this was a big problem for us until we solved this. And I think these 2 points are kind of related, wherein whenever you're writing data pipelines or ML pipelines, they have a very unique characteristic as compared to like other forms of engineering, wherein the bugs can go undetected. Like they will not raise a code error. If my data pipeline is generating like 0 aggregates, it's not going to fail. The pipeline itself is not going to fail. It's going to pass. If my model in my serving is generating garbage predictions, it's not going to fail. It's still going to just generate those predictions. So it's very, very important to test those components. I find like as a rule, we never write any data pipeline without a test. And we use Pydantic all the time because Pydantic gives us type checking. It helps us in catching those failures early on rather than, when we see user experience and then we're trying to debug what really happened. Bigquery, so I was just told that this is not true, but in my experience, like Bigquery can be very slow in production use cases. I think some Google Cloud folks will not agree with me, and I will work with them to figure it out. But this is what I've seen, and we have been trying to move to stuff like CockroachDB and Cloud SQL because Bigquery just fails for random reasons. At least that's what I've heard. Yeah, that's it from me, and yeah, you can feel free to stay connected and connect with me on LinkedIn.